Okay, so this is the last section of notes from this chapter. We started with sampling distributions in general. So we know the idea is we're taking all possible samples of the same size, calculating some statistic. We looked at, is that statistic biased or unbiased? Which just means in the long run, do we tend to over or underestimate or not? We looked at sample proportion because it's an unbiased statistic. Last thing we have to do is sample mean, which is an unbiased statistic. We talked about proportion is for categorical data, mean is for numeric data. This relates to the penny activity that we did. Do you guys remember the theorem that we discovered, kind of, or chatted about with the penny activity? The something something theorem? Okay, well, we'll talk about it. First thing that we're going to talk about is what are the mean and standard deviation of the sampling distribution of sample mean. So if we take all of our sample means and average them up, we're going to get the population mean. If we take all of our sample means and find the standard deviation, that is the standard deviation of the population divided by root n. If, though, our sample size is less than 10% of the population size. Only if the sample size is less than 10% of the population size. You need to know to check that. It is not on the formula sheet. You just have to know anytime we're talking about a sampling distribution, whether it's mean or proportion, we need to check that. To remind you, notation matters. So my advice to you is either use it correctly or don't use it. What I'm most concerned about are these symbols. So if you are not going to use that symbol correctly, that's fine, don't use it. Just put a number instead. But if you calculate standard deviation correctly, but then you attach the wrong symbol to it, you're not going to get credit. So I don't want us to lose credit because we write something incorrectly. So then both of these are on the formula sheet. What is not on the formula sheet is shape. Here is the little bit of a downfall for sample mean. There's not a nice way to check for shape. When we have proportion, how do we check that the sampling distribution is normal? Proportion has a nice check that we do every time.
There are 10 individuals in both groups. 10.
Yeah. What is the what do you write for it?
NP is greater than 10 and 1 minus P is greater than 10.
Okay. Do you guys remember doing NP is at least 10 and 1 minus P is at least 10? Okay, so that's for proportion. Mean doesn't have that. So the first question we're going to talk about is what is the shape of the sampling distribution of sample mean if we are looking at a normally distributed population? We're going to take a look at a visual real quick before we answer that. Okay, so what is the shape of the sampling distribution of sample mean when the sample is taken from a normally distributed population? Also normal. And it does not depend on size. Now, where people tend to mess themselves up is the different types of distributions. So I just want to emphasize one more time, there are 3 different types of distributions. The applet we just looked at, the top one was the population distribution. The second one was the sample distribution. And the last one was the sampling distribution. Distribution always means the same thing. What are the possible values? How often do they occur? Are we doing that for the population, for one sample, or a certain statistic? Okay, so let's do this example. At the Nutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding that the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. You guys have the right idea. So which one is more likely? Single jar. And if we want to know why, we said this, averages are less variable. Averages have less variability than individual measurements. So we would expect a sample mean, so that's an X bar of 10 jars, to be close to 16.1 ounces, which is the mean. So we're just going to finish these two, and then we will take a break. So we think or know really that a single jar is going to be more likely. What we're going to do is actually find the probability of each one. So we need to first find the probability that a single jar is less than 16 ounces. We're also going to find the probability that 10 jars, the sample, is less than 16. The one on the left, we already know how to do. We are told that the weight of the jars is approximately normal. So we would say, okay, we know that X is normal. The mean is 16.1, and the standard deviation is 0.15. Okay, where would I go in my calculator to do that? To calculate a normal probability, where would I go? Michaela? Normal CDF. So take out your calculator right now, do normal CDF. I want you to calculate this probability, please. Okay, I got about 0.2525. You guys agree? Okay, since we're being a little efficient here, I skipped a big step of this. If you were actually doing this problem in your homework or on a quiz or a test, what are you going to make sure that you show? The graph, right? We would show the graph and we would label it. Okay, so that's for one jar. Let's now find the probability that a sample of 10 jars has average contents less than 16 ounces. I want to point out to you what a lot of people miss. This is the key word, average. When it says average, that's how you know that you are using X bar. So average or mean tells us that we're using X bar, which means we actually have a little bit of extra work to do. First, what do we know about the shape of X bar? Well, if our original distribution is normal, then it doesn't matter our sample size. X bar will also be normal. The mean is unchanged. It stays 16.1. Here's where things are different. As soon as you are talking about X bar, the standard deviation changes. We are not using this 0.15 anymore. We're taking that 0.15 and we are dividing by the square root of n. Square root of 10. And now we're just back to normal CDF again. So go back, do normal CDF again, calculate this probability, please. Did we get about 0.0175? Now we said the single jar should be more likely, which it is. We okay on that? Okay. Last thing before we take a break. The most common error is that students use the wrong standard deviation. And it's because they forget to divide by root n. And this I'm going to be very, very specific about. What a lot of students will do is on this 10 jars question, they will have everything correct except on the figure, they use the wrong standard deviation. So they'll write this standard deviation in red, but then they use 0.15 on the figure. That's going to be counted as wrong. So you have to make sure you're consistent. This standard deviation that you calculated is the one that goes on the figure. So if we want to write ourselves a note, we would use that 0.15 divided by root 10 as the standard deviation on the figure. So it's really important that we note, or that we see, we're talking about a sample, and it'll say sample, and then it'll say average or mean. Last thing I want to address is what some students will do when they're answering part B is they'll say, okay, I'm going to find one jar, this 0.25, 0.25, and they'll take that, and they're like, well, I have 10 jars, so I'm just going to raise it to the 10th power. That is not going to give us the correct answer. What is this the probability of? It is a probability, it's just not the one we're looking for. What is that the probability of? Colleen?
All 10 jars under 16 ounces.
Okay. This is the probability, thank you, of all 10 jars being less than 16 ounces, which is not what we're talking about. We're talking about a sample. Sample mean. Some of them are going to be above 16, some are going to be below 16. We just want the average to be below 16. I know what you're thinking. This is all fine and dandy if the population's normal, but what happens if the population's not normal? And that's such a great question. That's what we're going to talk about. Okay, what is the shape of the sampling distribution when the sample is taken from a population that is not normal? Let's take a look. Okay, so if our population is not normal, for large samples, large being greater than 30, not equal to 30, greater than 30, X bar will be approximately normal. The word approximately is incredibly important. The AP test is very picky on that. If you say X bar is normal, you're not going to get credit. You have to use the word approximately. Did anybody have an epiphany of what that theorem was called? Something limit theorem? Started with a C? What? Central limit theorem. Write that down. It's a really important theorem. That's like the basis of a lot of statistics. For small samples, small being defined as less than or equal to 30, then X bar will follow whatever the population shape is. Mean and standard deviation are unaffected. Standard deviation is always found by standard deviation of the population over root n. Center will always be the same. Okay, so we've got one more example to do, and then we just have a few notation things to talk about. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assume that students at your school are typical texters, and you randomly select 50 students from your school. Part A, calculate and interpret the standard deviation of the distribution of X bar. So standard deviation of X bar is going to be the standard deviation of the population over root n. Standard deviation of the population is 35, and we're taking a sample of size 50, and I don't know what that is because I didn't do the calculation for us. It's about 4.95. So if we're going to interpret what that means, this is the spread or the variability about X bar. So if we were to take lots of different X bars. So to interpret this, I'm going to say in the long run, if we chose many samples of size 50, okay, we're looking at X bar, which is the sample mean. So the sample mean number of texts sent would typically deviate by 4.95 texts from the population average number of texts, which is 15. That 4.95, remember, is either side of 15. So it could be 4.95 above 15, could be 4.95 below 15. Okay, part B. What is the probability that these students have sent more than a total of 1,000 texts in the last day? So probability that the total is more than 1,000. Now, we don't know anything about the total. We don't have the mean, we don't have the standard deviation, we don't have a shape. So another way to think about this is if we have 50 students and a total of 1,000, that would be an average of 1,000 over 50, which is about 20 texts. So instead of thinking of this as the total being greater than 1,000, that is the same as the probability of a sample mean being greater than 20 texts. So then, sample mean, we don't know the shape, but we know the average is going to be 15. And we know that the standard deviation is going to be that 35 over root 50 that we already calculated. Now, the population is skewed right. So in this case, what we need to be thinking of is we took a sample of size 50. So because that sample is greater than 30, X bar is going to be normally distributed by the central limit theorem. Now, one thing that we did not check before, but we need to remember to check, is this is all assuming that our sample size is less than 10% of the population. So we took a sample size of 50. We don't know the population size. So if we divide by 0.1, our population would have to be greater than 500. We're taking a sample of students at our school. So it needs to be reasonable that there are more than 500 students at our school. That's reasonable. So we're going to say yes, there are more than 500 students at our school. I kind of ran out of room, so just write this down. Of course, we would draw a figure. And what I said before is remember to use the correct standard deviation. So on your figure, you should not be using 35. You should be dividing by that root 50, so it's about 5. Do you trust my calculation? If I just tell you what it ends up being? Okay, it's about 0.1562. Okay, quick note for us. If we were asked something like, what is the probability of one student sending more than 20 texts? instead of a sample, what is the probability that I take one student and find that that one student sends more than 20 texts? We cannot answer this. So a lot of people will say, oh, the central limit theorem applies. It does not. So X bar was normal. We don't know anything about one student. We know the population is skewed right, but that's it. So if we were asked something about one student, we would say we cannot answer this. Okay, we're not going to write this last stuff down, but you need to know the difference between all of these symbols. So, all of these three are population. Population mean, population standard deviation, population proportion. These are samples. Sample size, sample mean, sample proportion. And all of those are sampling distributions. So maybe if I'll label those for us. These three come from the population. These three come from a sample. These three refer to a sampling distribution. And last thing we're going to do real quick is if we look at p hat versus x bar, let's just talk about shape, center, spread, and conditions. For proportion, p hat is normal if, like we said, np is at least 10, and n1 minus p is at least 10. The center is at the population proportion. The standard deviation is that square root of p, 1 minus p, all over n. And we're looking at the 10% rule. For shape, for p x bar rather, either the population is normal or the central limit theorem applies. The center is just the population mean. The standard deviation is standard deviation of the population over root n. And again, it's the 10% rule. Center and spread are on the formula sheet. So you just need to be able to find them. They're on the back side. They both have the 10% rule. So really, the biggest thing you need to know is how to find the shape. Like I said, proportion is straightforward. You just check the two conditions every single time. Mean is the one that's a little bit harder because sometimes the population is normal, or you might have to use the central limit theorem. Ooh. Okay. Questions for me? No?